Greetings, building science enthusiasts, and welcome back to the Building Science Podcast. This episode is brought to you by Ultra Air, whole house ventilating dehumidifiers. Here at Positive Energy, we've been working with these dehumidifiers for years on many of our integrated mechanical designs, and we've seen such great results for both the health and comfort of our clients. We even have an Ultra Air dehumidifier in our office, and we absolutely love it. When you're working with an airtight and well-insulated building, you quickly notice the outdoor air infiltration restrictions that occur, which allows pollutants and moisture levels to accumulate inside. So when you think about it, properly controlling that moisture in your home will definitely improve the effectiveness of your air sealing and insulation efforts, and will definitely improve the health and comfort for your client, your family, you. Just imagine being able to run your air conditioner at a higher temperature without feeling uncomfortable, and knowing that this improved comfort is coupled with fresh filtered air. These are just a few of the many benefits of incorporating the Ultra Air dehumidifiers into your home or your project. It really is an easy choice to make. To learn more about the best strategy for controlling moisture in your home, check out ultra-air.com, that's air with an E at the end, and see how a whole house ventilating dehumidifier can work for your home or project.
Welcome to the Building Science Podcast.
Welcome to the Building Science Podcast.
Bringing the human factor to construction, design, and architecture. Brought to you by Positive Energy in Austin, Texas.
Okay, hello and welcome back. Welcome back to the Building Science Podcast. I'm Kristof Irwin with Positive Energy, and today we are talking about a very important and often overlooked subject, and it is the air distribution system. We exist in an industry that often has somewhat of an out of sight, out of mind, or at least out of sight, not so important perspective on things. So today we're going to be talking about what is accurately considered the lungs of the building, the pulmonary system of the building. Or possibly more accurately is to call it the heart and lungs of the building, the pulmonary system and the cardiovascular system, or the circulatory system. And the reason I say that is because, let's think about our bodies, right? We have our skeletal musculo system, and then we have all these fluids that need to circulate inside our body, and together they make this functional thing. We have a very strong analogy for buildings. So I'm going to start out talking about the building enclosure here at this introduction, and then talk a little bit about the circulatory systems and how these two work together. And then we have some guests coming in that are going to be talking about the business of improving the pulmonary system of the building. And sadly, this is often overlooked. We can get into it when they arrive, but there really is nothing more important than making the building healthy and comfortable. And there's nothing more pivotal for that than a properly designed and functioning air distribution system, as we shall see. Okay, so part one is enclosures, and then we'll talk about ducts, and then we'll bring our guests in. So let's start by looking at the building enclosure. And we've talked about this before. In fact, we have a series of 5 episodes on the enclosure, on the control layers, rain, air, vapor, thermal. We know a lot about that. Don't worry, I'm not going to go that direction now. What I do want to point out is that if you're in a building right now, look around you, right? So the walls, the ceiling, the floor, they seem to be just sitting there doing nothing. But as we know, you guys that are listening to this are a self-selected group of people that know that is so not the case, right? The enclosure, the walls around you, the ceiling, the floor, it's constantly and it's dynamically mediating heat, air, and moisture flows, right? So the word mediating is actually important in there. It is the middleman. It's not controlling the flows, but it is controlling the dynamic of those flows. And what I mean, I guess, is that the building is sitting in a sea of heat and air and moisture flow. And keep in mind, cold is just the absence of heat. So we can say it's sitting in air of some temperature, there's a certain amount of mass around the building, and there's moisture in it. So your building's sitting in this soup of heat, air, and moisture. And how it moves through the enclosure depends on a combination of the driving forces that can move these things through the enclosure, the material properties that the enclosure is made out of, and then how those materials, how those assemblies work, right? So like, are your walls leaky? And if your roof is leaky, is it leaky, between the ceiling and the attic, or between the attic and the outside? Things like that. So what's very important to realize is that a building is constantly and dynamically adjusting itself based on driving forces. One of the most potent and regularly operating driving function, we'll talk about this when we get to ducts a little bit more deeply, is your air conditioning system or your heating system, right? We've got a fan in there that's able to suck air out of the space and move it all around the space and put it back in. That fan is powerful, right? There's a reason why Energy Code is saying we need to make our air conditioning systems or heating systems run less to save energy. It's because those machines are moving tens of thousands of pounds, sometimes hundreds of thousands of pounds of mass around your building every day. So these are no little tiny pumps. These are big, powerful pumps, these fans and these air handlers. So that's the basic view of the enclosure, is that it is constantly and dynamically mediating heat and moisture flow, and we think about it mainly from inside to out, but that's not true. So let's think about the home a little more fully, right? So the home, or a building, any building, is actually a set of three-dimensional volumes that are connected to each other. And now at the coarsest level, you could say that these three, let's just say pick a typical house like on a crawl space with an attic, right? You have three main volumes. You got the crawl space, which is a volume of air, and you've got the conditioned space, which is a volume of air, and then you've got above it, you've got an attic, which is a volume of air. So that's pretty easy to understand, and clearly we don't want to have airflow between the crawl space in the house, if we can avoid it. We certainly don't want to have it in a way that we don't know where it's coming from and where it's going to. And the same thing with the attic. We'll touch on that in a little bit. So the home is an interconnected group of three-dimensional volumes. But check this out. It is so much more than those three. Every stud bay. So stud bay would be a three-dimensional volume that's in between two studs in your wall. And it has, a bottom plate on the bottom, a top plate on top, sheetrock on one side, and whatever your sheathing is on the other side. So it's this long, skinny, rectangular volume in the wall. And there are hundreds of those surrounding you when you're in your conditioned space. Whether the air can move into and out of those three-dimensional volumes, those stud bays, that's a big deal, right? When I was testing production homes, I had a little borescope, and we would get into these relatively new production homes, and you could look inside the walls near like the light switch next to the front door. And you could turn the light around, and you could see that there was already starting to be some light fungal growth on the back of the sheetrock inside there. So I use this as an example to show that what was happening there is you had a light fixture on the outside, which means that there was a hole through the sheathing. And then you had this stud bay. And then often in the same stud bay, you had the light switch on the inside or the doorbell button on the inside. So now what you have is a path from inside to out, and anytime there's a pressure difference between inside and out, air will move from there. So most commonly what happens, and we'll know why in the next few minutes, most commonly what happens is your air conditioner comes on, the house goes at a negative pressure, it sucks the outdoor condition into the wall, it sucks the wall into the house, and there you go. And that can be prevented. So we have these thousands of interconnected three-dimensional boxes, right? Some of them as big as the back of a semi, a container box. Some of them are as small as a shoebox. These boxes don't end at the stud cavities. These are rafter bays if you have a vaulted ceiling. These are thermal bypasses, which are like kind of like an unintentional laundry chute that goes between the attic and deep down into the walls of a house. You can have air moving from outside the outside wall into the space around your bathtub. That's very common that people didn't air seal that properly. The space behind your kitchen cabinets, especially if there's an outlet punched through there, right? So the house, you just need to remember to kind of recalibrate your thinking to, okay, I'm in this building, I'm in this home, and this building and home is a whole set of boxes connected to each other. And the air quality in some spaces is very, very poor, like your attic or your crawl space potentially. And the air quality in the other spaces is what you want to be really good. So you never want to be confused about where the air is coming from and why. So the HVAC system is, again, boxes, right? You have these I guess you could say they're like small refrigerator-sized boxes, something like that. And those have the fans in them. Those are either your furnaces or your air handlers, your heat pumps, so furnace or a heat pump. And friends of the podcast know that we are still using gas to heat and cool homes, and that hopefully that'll be occurring less and less over time. There's a lot of people that, without trying to be malicious, they just know what they know, and they don't know what they don't know, and they're always used to putting gas furnaces in, so they keep doing it. But just to keep it pithy, always, always, always avoid putting combustion in your house if you don't have to. And when it comes to heating water and heating air, you don't have to. So stop doing that. But the point is, you have this box and it has a fan in it. And that fan does something that's seemingly simple, but it's actually it's quite profound. It violates a law of physics. What it does is you have air moving from a low pressure on one side. That's the air gets sucked into the box because there's a low pressure, so the air moves to that. Goes through the fan, and now it comes out at a high pressure. So the only way that you can do that is to put energy in. You have to put some electricity in to spin a fan. So you have air moving from a pretty powerful low pressure to a pretty high pressure. And when I say pretty powerful, what I mean is relative to what other fans in the house can do, like your bath exhaust fans, your range hood fan, your dryer is a big fan. Those create pressure differences, but nowhere near. Roughly an order of magnitude down from these big fans. Now, there are also, while we're on the subject of what creates pressure differences, there are stack effect and wind effect pressure differences. And on high-rise buildings, the stack effect and the wind effect can get very high. So that's a big thing. But today we're talking about where most of you spend your time, which is in your home. I think we all know that you spend 70% of your time on average in your home. So there's probably no more important place to be careful about air distribution. Multifamily buildings too. Okay, so back to the HVAC. We have boxes that are connected to other boxes, right? So I have this box and it's sucking air out of one side and pushing it out of the other. That's my air handler. And then on each end of that I put other boxes. So I put on the side that's sucking, I put what's called the return plenum. It's a box. And then on the front end I put, on the supply side, on the side that's blowing, I put a supply plenum. And then I connect those to what would really seem like kind of the cardiovascular system, right? It would have tubes that branch off into smaller tubes. And those are your trunk lines, those are your runouts, things like that. So those are ducts. And commonly in our market here in Austin, Texas, those two boxes on each end of the air handler will be made out of duct board, which is a fibrous material. It's not the best product for it, but it is optimized for ease of installation. It has some good acoustic properties, and it has some good financial properties. Same thing with the ducts, right? We use a lot of flex duct, which is a spiral slinky wrapped in something like a saran wrap with insulation and then another layer on the outside. And just by its nature, right, it's a spiral. So air moving through a spiral is creating a vortex, and that vortex is like a self-flow restricting situation. So if it's as though we said, let's think of what not to use to distribute air, and then used it. But it is affordable, and it is very common, and it is good for insulation because it's pre-insulated. Okay, so I'm getting a little bit deeper into it. I want to just basically say the HVAC system is boxes and tubes, and then it goes, and this is an important spot here, it goes to another box which is called a supply bucket. So the air is moving out of the air handler, it goes into the supply plenum, it goes through this tube, your duct system. Now it gets to the room and it's about to enter the room. It's either going to enter the room from a high sidewall, which is preferable, but takes more pre-planning. So often it doesn't. Often it enters the room from either the ceiling or the floor. Ceiling in a cooling-dominated climate like Austin would be better than the floor. But the point is that this duct terminates in another box, and that box sits behind your sheetrock. And then on the other side of the sheetrock is your diffuser. And keep in mind, you do want a diffuser. You really don't want a grill. You really don't want a register. And what makes a diffuser is it has a design based on fluid dynamics so that it actually can throw and mix the air. And it has the ability to control the mass flow through itself. So it has a volume control damper, which controls how much gets through and therefore how fast it goes, the fast being an important part. So we have boxes going to tubes, going to boxes, going through a diffuser, and we're in the room. Now here's the part that people often forget about. The system operates in a loop, right? So I've pushed the supply air into, let's say, your living room, and that supply air needs to make its way back through to the return. And it does that by traveling through the conditioned space. So when you hear people like us say, the enclosure is the HVAC system, that's what we're referring to here. Is this air conditioning system is a loop. The air is constantly looping around, lap after lap, getting hot or getting cold, depending on the season. And it absolutely moves through the conditioned space. Now, let's put it all together and talk about why having airtight distribution systems is so important. So we have this enclosure that air can move from box to box. This enclosure is a series of interconnected boxes. We have this duct system, which is a whole bunch of discretized components that's threaded through this series of box to box. And we are moving, let's say, tens of thousands of pounds of mass through this system. Meanwhile, the enclosure, by the way, can hold hundreds of thousands of pounds of mass. But let me just give you a real-world example, and then we'll bring in our guests. So this is a scenario that actually creates the language. Those of us that are into building science, we often use the language bearing witness. And, I chuckle a little, but it's really quite sad. It's as though we all want our cars to be energy efficient, but only a few people know that they all have underinflated tires and their emergency brakes half on, right? So that's what we have with buildings. I'm going to describe a scenario right now that is undoubtedly occurring tens of thousands of times here in Austin and probably tens of millions of times across the United States right now. So here goes. So we have an air conditioning system in an attic or a crawl space, and it leaks. There's no way around it. It's made of physical reality, and there's connections. Each connection has the ability to leak a little bit. But what are the properties of this system? So what it has is a return duct on one end that is usually a big duct going right to the space. So really there's a connection at the air handler or at the return plenum and a connection at the space. It's usually just one. So we have those two connections on the return side. And then it goes through the air handler, goes into the supply side. Now check this out. It's connected to the supply plenum. There's a connection there. It connects to the trunk line. There's a connection there. Connects to the runout. There's a connection there. Often these runouts split into Ys, which have 2, 3 connections at each Y. Then it goes to a bucket, and there's a connection there. Then the bucket to the sheetrock. Ding, ding, ding. Very important connection there. That's often leaky. So then you go to the diffuser. It can leak there. So what you have is a very asymmetrical system in terms of the amount of leakage likely to occur on the return side versus the amount of leakage likely to occur on the supply side. Why does that matter? Well, let's go into the conditioned space and see. So if you're inside your house, you are sitting in the living room, let's say, and there's two things happening. The return is sucking air out of your house. The air conditioner's on. Return is sucking air out of your living room. The supply is putting air into the living room. So let's just keep it simple and say it's a 2.5-ton system, which would mean it's moving on the order of 1,000 cubic feet per minute. Right? So 1,000 cubic feet per minute. I don't want to trivialize that. Let's divide by 13.5. So that's 74 pounds of air per minute. So every hour that thing's running, that's 4,500 pounds of air getting sucked out of your house. So you've got 4,500 pounds of air getting sucked out of your living room. It goes through the air handler, and now it hits a whole bunch of potential leaks. Austin has been measuring the leakage of existing homes, and the average, I believe, is like 27%, I think is the number. So I'm sucking 4,500 pounds of air out of my house every hour, and if I'm leaking 30% of it out on all these supply leaks, that means I'm putting in 3,000 pounds of air. So let's say your bank account was losing $4,500 every hour and you were getting $3,000 in. What's going to happen? Very quickly, your bank account's going to go negative. So same thing with the pressure in your house. When you are sucking more air out of your house than you're putting in, your house goes negative. We say that means you've depressurized your house. So why is that a problem? Well, now we bring in those connections of boxes. So let's just say the very typical scenario. Well, let's just say that's what's happening. You have your equipment in the attic. You have insulation on the attic floor or just above the ceiling sheetrock, and your air conditioner comes on and the house goes negative. And the connection between that supply bucket and the ceiling sheetrock is not well sealed. So what happens now? You get all sorts of fine and ultrafine particles and bioaerosols put into your space. Why is that a problem? Because those aerosols go into your lungs. They can be endocrine system disruptors. They can just be particulate matter triggering asthma. It's a big problem. It's a huge health problem, but we'll leave that for another podcast. So health, the health of you and your family, you and your coworkers, absolutely depends on avoiding building depressurization. And you could see, if you listen carefully to that scenario, what the problem is that there was a lot of leakage occurring on the supply side. So as long as supply side leakage exceeds return side leakage, we're going to suck the air. We're going to be depressurizing the house. We're going to pull air from an adjacent volume. Keep in mind, it's not just the attic in that scenario. It would be it would be pulled through that light fixture. You'd suck the air through the light fixture on the outside into the wall, and then you would be sucking the air from the wall into the house. You combine this scenario with the fact that we don't control humidity well, and we have large populations of dust mites in wall cavities, and dust mites and dust mite feces are, again, known asthma triggers and sensitizers to allergens generally. So you have tens of thousands of people in Austin, probably tens of millions of people in the United States right now that are on some sort of medication because they have chronic sinusitis or chronic rhinitis or worse, asthma or sleep apnea or something like that. And it's entirely preventable. And one of the key ways we prevent that is making sure our air distributions are tight and functioning the way we want them to. The other thing is, it almost seems trivial next to that, right? This whole crazy epidemic of needless, pointless pain and suffering and medication expenses and time at the doctor and lost productivity. Next to that, though, there is a reality that if your ducts if they're leaking, you're going to be uncomfortable. You're potentially going to be very uncomfortable. If you're not getting the air, let's say, to your master bedroom that you need to keep it cool or warm in the winter, well, that's a problem too. And now I'll bring in our guests. So I have with me today Ian and Sean Harris. They're the co-owners of Aeroseal of Austin. I should do full disclosure. Sean Harris and I have been building houses together for about 16 years. Well, we built houses together for a while, right, Sean? And he's works for Positive Energy, which is somewhat of a progressive do-goodery firm in the society, and Sean has one of those as well with Ian, with Austin Aeroseal. They are fellow do-gooders, and they're previous podcast sponsors, so thank you and welcome. So I'll let you guys introduce yourselves and introduce Austin, Aeroseal of Austin.
Good morning, Chris. Thanks for having us.
You're welcome.
So my name is Ian Harris, and we've been working on our business, Aeroseal of Austin, now for 6 years. It has been quite the road. In the beginning, we started off and we were more dealing with people that had consequences of their actions or the builder's actions from leaky ductwork, and they suffered the consequences of those actions, and then ultimately we were called in to seal those ducts. The way I see the business going in the future is ultimately it will switch around and people will be more proactive on looking at the testing of those ducts and getting us to seal before the consequences hit.
Yeah.
And therefore having a much more healthy, more energy efficient home.
Mm-hmm. Yeah, I really hope that pushing the health angle is going to be more of a lever to move people's attention to this stuff, because apparently energy doesn't push it quickly enough. Yeah, so the energy codes, in fact, Sean, have some basic requirements for air sealing. It's pretty simple, right?
Yeah, it gets a little more complex, Chris. Thank you for having us, by the way. So initially in Austin, we adopted the 2009 IECC, where the leakage was 10% of the airflow. So you have, let's say, a 2-ton unit. The airflow on that typically is 400 CFM per ton. 10% of that for 2 tons would be 80 CFM that you would be allowed. Now, the City of Austin was very smart in what they did. They realized that in our hot, humid climate zone, you want to slow down that fan, and you want to have that fan running slower so that the air conditioner will run longer, the coil will be colder, and you'll be able to dehumidify more. So they thought, if the fan is running longer, that means that there's more chance for duct leakage, and so therefore we should adjust the amount of duct leakage you're allowed to the 10% of the reduced airflow rate at 360 per ton. So in this case, a 2-ton unit would produce 720 CFM, and so now you'd only be allowed 72 CFM of leakage instead of the 80. So from there, the city then adopted the 2015 IECC code, which requires 4% of the square footage in leakage. And part of the reason for the change from 10% of the airflow to 4% of the square footage is because you could get people who would sort of game the system. They would go, if I put in a bigger unit, I'm allowed more leakage. And if I'm allowed, like let's say in that same situation, they put in a 3-ton, well now that's 1080 CFM, and now they're allowed 108 CFM in leakage as opposed to the original 72. So they switched to the square footage to try and stop people from oversizing their equipment. The smaller the equipment you can put in, the longer it's going to run, the more efficient it's going to dehumidify the space. Obviously, a manual J-load calculation is always needed in those situations to figure out exactly what the size is, but you never really want to oversize too much because you'll run into comfort issues.
So 4%, do an example of 4% of an enclosure.
Yes.
So like a 2,500 square foot house or something?
Yeah, well, I guess with the same 2-ton to 3-ton analogy, a 2-ton unit, depending on how much square footage you could serve with that, how efficient your building is constructed, the old rule of thumb was 500 square foot per ton. So if we looked at things old school, a 2-ton unit could service 1,000 CFM, 1,000 square foot. But nowadays, with better enclosures, better insulation, we can actually get away with a lot more than that. And it varies depending on each building, obviously, and a manual J needs to be done to figure that out. But roughly 800 or 900 square foot per ton would be a reasonable amount. So technically a 2-ton could service a 1,600 square foot building quite well. And so now you're looking at 1,600 square feet. I guess we'll just do the math on that.
I think it's 64.
4% of
1,600 times 0.04, 64.
Yeah, so now that same 2-ton is allowed 64 CFM instead of 72. But that's if you have all of that extra square footage. If you don't do that and you're looking at the 500 again, now you're looking at you needing to be under 42 CFM instead of the 72. Let's say we used 500 square foot per ton. So it does reduce it quite a bit, which is important. And also important to know that every time the city reduces their duct leakage requirements, making it harder and harder, the test more stringent, the AC companies just barely pass, just barely get it down. So back in 2009, the code was 10%, and they were just barely getting to 10%. Now we've shifted it down a little bit, and they're just barely getting to that 4 CFM per 100 square feet. So the idea is that the code is slowly working people down to get more and more efficiency out of the ducts. And I think that that's a really great way of doing it, sort of ease people into it. Because if you immediately said nobody can have any leakage, everybody would throw their hands up and say, what's the point? And that's not how you want to run the system.
Yeah,
so.
Absolutely. So Sean and I, Positive Energy in its original incarnation was in fact a performance testing company. And Sean and I were out on many, many job sites, and we would get the, hey man, quit busting my butt, you keep failing me. And we would try to be calm about it and say, no, in fact, we're measuring you. We're just measuring you. We don't fail you. You simply need to get the value you paid for your contractor to do that sealing. And I'd like to point out, there's something called the Ring 4 Club. And if you want to Google Ring 4 Club, Ring 4 refers to the duct leakage equipment. It's called a duct blaster, but don't worry, it does not blast your lungs, ducts. It puts it at less pressure than it operates at, typically. But you put these rings on it as part of the operation to test leakage. And people that are getting into the Ring Floor Club, they're getting like less than 4 CFM of leakage?
Yeah, so the different rings, basically, the smaller the ring that you can use, the less airflow you need to be able to pressurize.
That's right.
And so the smallest ring that they make is a Ring 4.
Well, actually, Ring 3 on the standard equipment, but you can order.
Exactly, yeah. So to give you an idea, Ring 3 has a range of between, let's say, 15 CFM and 200 CFM. So predominantly when I'm testing with Ring 3. If you get below 15 CFM, in order to accurately measure it, you're going to want to switch to a Ring 4. So HVAC contractors that can get into the Ring 4 club mean that they have duct leakage that is less than 15 CFM, which is just amazing. And it's I've been lucky enough to measure a few that are below 15, but not very many actually make it. It's just a hard test, hard thing to pass.
All right, so now there's two more directions I want to take this. One is the business side, and we'll put that off to the side now because what we're talking about is leakage. But the second is leakage, right? This Ring Floor Club, this idea that some contractors can do it and some contractors can't. And it's not like, oh, it's just as simple as some are skillful and some are klutzy, or some care and some don't. I mean, really, right, Sean? It's not as simple as that. You can get a disciplined, hardworking, very ethical contractor that endeavors to do their best, and it's a bit heartbreaking when you go measure them. I mean, we don't want to fail them. But could you give any tips to contractors or to builders that hire contractors? So when the contractor tells the builder, look, your best scenario here is just to hire a different performance testing company because all you need is a PDF file saying you passed. You don't really need tight ducts. I think any builders that are listening, that's so not true. That's so not in your interest or your client's interest. You need tight ducts for the health and comfort of your clients and for your brand reputation. But it might seem like all you need that day is a PDF file saying you're passed. So anyway, anything come to mind?
Yeah, well, so first, one of the analogies that I really like using, and it applies to both new construction and pre-existing homes, is imagine air is a fluid. So imagine if it were water. You know, how tight would you want your ducts if it was water that was in them? You would want them watertight. And so how tight do you want your air ducts? You want them airtight. If you had a water leak above your ceiling, you would see that it's dripping onto the back of that sheetrock, and eventually the sheetrock would degrade, and you would see a noticeable problem. And if you see it, you would then go, oh, I've got a water leak, I need to get that fixed. But because it's air and we don't actually see it, then we have to wait.
The house is already filled with air.
Right, exactly. Yeah, you just don't know that your ducts are leaking. You have to wait for some bigger problem to occur for you to go, oh, wow, I have a really serious problem. And sometimes that happens subtly with asthma and sleep apnea, things like that, some respiratory issues. And other times it's I've got mold in my house, or my wood floors are cupping, or I can't manage my humidity, or I'm uncomfortable. But those things you can then sort of blame other things because it's not a direct correlation sometimes as if it were a water leak. You know, it's pretty obvious when you have a water leak for the most part. So if we start thinking about air as a fluid, I think that helps a lot in both remodel situations, in existing homes. All homes have duct leakage, but also in brand new construction and how contractors need to seal their ducts. Pretend that is water that's going to be in there, and you need to seal every single seam as tight as you can. And so I guess some advice to contractors who are
there common seams?
Yeah, so sealing ducts, it's funny actually. For something that is supposed to be airtight, the tools that are given to you are the leakiest that they could be. Chris was talking earlier about the bucket that's on the back of the sheetrock. That bucket has 15 seams, none of which are sealed, and all of that needs to be sealed by hand after the fact. And if they came pre-sealed from the manufacturer, I think it would cut down on a lot of that. I'm not sure why. I guess it's a cost thing as to why
they do make styrofoam buckets that have no edges and no gaps.
Yeah, the styrofoam on the outside still leaks underneath, funnily enough.
Oh, wow.
Yeah, I've tested that.
Interesting. Then the sealing of this bucket to the sheetrock is...
Yeah, and then sealing of the bucket to the sheetrock, that's the final thing, and definitely something a builder could check to make sure all you have to do is take down a register or a diffuser if you're really good, and see the back of that bucket where the bucket hits the sheetrock. And if there's a gap there, even a really small, thin gap, you're going to want to cover that with caulk and make sure that whole thing is sealed airtight.
And also, if I may just interject there, a lot of times when it comes to that bucket to the sheetrock, nobody really wants to take responsibility for making that happen. Mm-hmm. The air conditioning contractor has come in, he's done his bit. The sheetrock people have come in and done their bit. The decorating people have come in there, done their bit. Everybody's about ready to put the registers on, and nobody's really done that final seal. The air conditioning contractor probably doesn't have an opportunity to come back and make that happen, but it really should be down to the general contractor to ensure that at some point during that process, those buckets do get sealed.
Absolutely, yeah. It's a critical one. And it's a big leak. It's
and
it's a potentially large leak.
Right, and so each bucket, if the sheetrocker is good and the sheetrock goes right up to the bucket, you're still looking at maybe 3 or 4 CFM per bucket. If the sheetrock's bad and you've got big gaps there, it could be 10 or 20 CFM per bucket. But think about how many registers you have in an average home. Let's say there's 20 registers, each of which are leaking 3 or 4 CFM. Well, if it's leaking 4 times 20, that's 80. That's already failing the test, no matter what size unit you have.
Yeah.
So being able to do that and seal those, it's like death by 1,000 cuts. There's so many little places for leakage that you just have to really be thorough and methodical and have a system in place for when you're sealing.
I want to interject too, so I want to get back to that because there's some more places I think there are common leaks. But this idea of, let's say you have a sealing supply register and you have a small gap between the attic... small gap between the bucket and the sheetrock. So that means you have this little crack between your conditioned space and your attic. And you have air whooshing through it every time the supply plenum comes on. That air is going to entrain adjacent air, and it's going to suck a little poof of air the whole time it's running from the attic into the conditioned space. And check this out. Where are the smallest particles, the ones that are the most damaging to indoor air quality and most damaging to client health? They are going to be at the bottom of the layer of insulation that's in the attic, which means they're going to be just above the sheetrock. They're going to be right around that gap. So, and it's not like you're going to suck that particle through and then it's clean, because the insulation, its physical reality has a thermal expansion coefficient. So over the seasons, over the day, it's expanding and contracting a little and it's flaking off. Meanwhile, there's also probably critters pooping up in there. Their poop dries out and turns into dust and it falls down there, and roaches are... Yeah, a lot of nasty stuff. So let's follow it around. So we came through the bucket. We had the crack around the sheetrock. Definitely seal that. The diffuser goes on. Now, if the crack around the sheetrock sealed, the diffuser doesn't need to be sealed to the sheetrock. Although sometimes it is, but it doesn't need to be. Now you have the conditioned space. And, there's a whole other podcast on the enclosure. You want to make sure that conditioned space isn't pulling air in inadvertently. And now it goes into the return plenum. And that is a big one there too, right? So if there's a crack around the return leak, not only are you going to measure that, but you have the opportunity to suck dust from your attic right into your return. So is that one you see leaky a lot?
Definitely, quite a bit. Depending on the construction, if your unit is located in your attic, which we all advise you not to do. You don't want to try and make ice in an oven. You want to put the equipment inside your conditioned space. So a lot of times, if it's not in the attic, it's in a closet. So it's an upflow unit that's in a closet. And the units that are in a closet like that, not enough. Not enough priority is given to the mechanical equipment, and therefore you're typically working in a really cramped space. And so that cramped space means that it's going to be hard to access underneath the equipment where the return might be. It's going to be hard to access behind the equipment, but that return, whether it's in the attic or whether it's underneath the unit there, it's really easy for those seams to get missed right at that sheetrock connection if it was in the ceiling, or have someone crawling in and getting all the seams 100% on the inside of that upflow return plenum. yeah, it's just, like I said, it's about being methodical and about knowing where those things are and really making it a priority to, one, get the proper space you need to seal, but also being able to know all of the seams. For example, a lot of times you stick your head into a return plenum underneath the unit, and you're looking around and everything seems sealed. Well, how often do you turn upside down around and look behind you at the seam that is above you? Essentially, when you're looking in right behind your head, that is an often missed seam because you just aren't thinking to look behind you like that.
Yeah.
So.
Yeah, and that's if it looks good.
And that's where the camera on the phone really comes in handy, because you can just put your arm in there, snap some pictures,
Or a little video.
blow it up, and you can see all those holes and cracks.
Yeah. So I remember Sean and I were following this spec home developer around East Austin years ago, and the return plenum, we were doing his testing, and the return plenums were always leaky, so much so that, not subtle like you were saying when we first got there. Remember, you'd look into the return plenum, and you would see wall studs. So basically, straight to the attic, so you're at the bottom of the return plenum, which is on the floor of the first floor, and I'm looking at, there's this stud. This is getting back to the interconnected series of three-dimensional boxes. So one of these, the homeowner had said, man, my air quality is bad, had put a stronger filter on the return. So in putting a stronger filter, making it harder to pull air from the conditioned space, this client was getting more air from the attic. Kind of tragic, actually. 3 kids, 2 of them having asthma. But let's get back. So we're following it. We've got the crack around the return plenum. Duct. The return duct connects to the return plenum, leaks there, and then the return plenum itself connects to the equipment chassis.
Yeah, and probably the next most common thing that I see, HVAC contractors all know they need to mastic the seams where the equipment meets both the supply and the return plenums, and they do that, but one of the first places I go to look for duct leakage is underneath. In the attic, it's going to be hard for them to stick their hand all the way under and get underneath that unit to get that last seam. And a lot of times what happens also is they'll get under there, but the weight of the mastic that they're putting on outdoes the adhesive on the tape. And it basically just weighs it down and falls open. And so now it's hanging open underneath, and that's when all of your attic air basically is being sucked into the return, or you're just blowing out on the supply. And
water can get there on the supply side.
Definitely. So if you've got that cold air running past now what's a hot surface, you're then going to get some condensation on there, which could then turn into a bigger deal.
Science
for
project.
air quality. Exactly.
Mold project.
Yeah.
Well, and on a lot of the older houses, older construction, people will use those plenums to sit on, crawl over, and that also destroys that seam. So, you have to really monitor that and make sure that that's all sealed up.
And if you're in an upflow unit, so if you're in basically a closet inside the house with the equipment, one of the hardest seams to get to is the back seam. A lot of times not enough room is given to this mechanical closet, and so the equipment takes up all of the space, and you can't access the seams that are directly on the back side of that unit. So that makes it really difficult to get everything airtight at all the seams, whether that be where the furnace connects to the platform of the return plenum, or where the furnace connects to the coil, or where the coil then connects to the supply plenum. All of those seams in the back are really hard to get to.
Out of sight, out of mind again. Okay, so let's keep in mind, everyone listening, that we just talked about how hard it is to get to it and how hard it is to see these leaks. Because the next thing we go, now we're at the supply plenum, and we're going from there to the buckets. And now you have like a branched network, right, of kind of like the trunk of a tree splitting into the big branches and the small branches and the twigs and all that, finally getting to the supply. Following all those around and trying to find all the little tiny leaks that could be on the bottom or hidden, or almost an unworkable situation in an existing home to say, I'm going to hand seal all these with a brush and some mastic and a tube of caulk. So this is where the name of your company comes in, Aeroseal of Austin, right? I think this is a good time to introduce what, in fact, Aeroseal is.
Yeah, so Aeroseal is a product that was developed at the Lawrence Berkeley National Labs out in California with funding from the Department of Energy. And basically the government got behind this big push to seal up people's ducts because they wanted to not have to build any more power plants. And so if they raise awareness about duct leakage and everybody seals their ducts, everybody's going to use less energy. And I guess the side effect of using less energy is you're also more comfortable and you have better air quality. So it's it all goes hand in hand. So what it is an aerosol that you spray into the ducts under pressure. So you block off the equipment and the registers, and you create a pressure and a flow inside the ductwork. And then when you introduce this aerosol, wherever the material wants to sort of leak out, it will bond on the edges of that leak and then start sealing up. And it seals holes up to 5/8 of an inch automatically. It's similar to Fix-A-Flat for your car tire. It just goes in, finds the leaks, and as long as we can pressurize, we seal down ducts really, really tight. Pretty much airtight at that point.
Basically magic.
And what I love about it is it's beyond code. It doesn't matter what the code is. We are so much tighter. And perfect example was yesterday. In a hotel, we were sealing up a duct that ran 33 floors. They could not pass. They were leaking so much. And we hooked up our equipment. They were in excess of 1,200 CFM of leakage. And we got them all the way down to, was it 7?
Yeah, so they had
1,200 to 7.
They had 1,200 CFM. Passing was 300 CFM. So we just had to get them to 300 CFM to pass. We ended up getting them down to 17 CFM or something
17,
like that.
Okay.
Yeah, so it's like single digits. The day before we got down to 7.
Oh, that's right.
Yeah,
Sorry,
yeah.
Ah, okay.
So yeah, it is significant. We don't when we go in and seal, we don't worry about what code is. We're more concerned with, can we get it to 0? Can we get it to 10 CFM? In the older homes that are more leaky, the average is probably between 20 and 30 CFM that we get every system down to, no matter what size or what's going on. So.
I want to make a quick comment here. You guys, this is a podcast. There's no visuals. I'm looking at Sean and Ian, and Sean has mastic in his hair, mastic on his shirt. They've just gotten out from an underground duct, sealing it this morning. This is not like the glory job, but it is so important. I mean, what these guys are doing, these are the unsung heroes of the industry, and yeah, we need to embrace what they're doing. A little bit more about Aeroseal. I don't want to get down into the weeds of exactly how it works, but the basic scenario: you connect your equipment, and then you put the system under test right then. Is that right? How's that go?
Yeah, so the 3 pieces of equipment that are necessary for Aeroseal. First is a heater. In order to turn a liquid into an aerosol, you need hot airflow going through, a hot, dry airstream. That way the air is lacking moisture and will want to accept more moisture into the air the more energy it has. Mm-hmm. So we have a heater.
It looks like a giant blow dryer. I've seen it.
Yeah,
yeah. Literally, like the red coils.
Exactly. There are heat strips in there. The next piece of equipment that connects to that is a fan.
How big around is this?
Yeah, it's about, I think, 18 inches. We use 3-foot lay flat. Turns out to be about 2 foot in diameter that hooks up to the actual ducts. And then that 2-foot lay flat hooks up to this heater. And then from the heater, the next piece in the puzzle is the fan. And this fan is what we use to pressurize, but also create an airflow inside the duct. We want airflow because we want to circulate the sealant when it gets injected into the airstream. So from there, this fan has like a measured opening on the back, and it's hooked up to a manometer, and the manometer then measures the pressure inside the duct and the pressure at the fan, and we can measure the amount of leakage that we have while we're sealing. So every minute we have the computer plots a graph. So that's the final piece of the equipment is a computer that sort of runs the whole process. So we've got the computer hooked up to the manometer, also hooked up to the fan and the heaters, so we can measure pressures, humidities, temperatures, all of those things all at once, and we can then plot graph points that will eventually hopefully get to 0 as we continue sealing.
Excellent.
One of the other cool things about it is many times we've come across things where the sheetrock people have sheetrocked over a bucket, and the register is on the other, the bucket is on the other side there, but it was never cut through and opened up. Another time, in between floors, there was a duct that was never attached to the bucket that went to the utility room. And we were fortunate, across the hallway there was the bathroom, and in there we were able to take out the fan out of that bathroom and then put in a scope so that we could see what was going on. We could see the fog from the aerosol. And we knew that it was about 80 CFM that we were leaking, and we couldn't seal up. And sure enough, there was this whole 8-inch duct that was going to the utility room that had never been connected. And so we just cut a hole in the sheetrock, connected that duct. Unfortunately, they had to call in a sheetrock guy to patch it and everything else, but now it was all done and sealed. Mm-hmm. And so the point is that because of that constant computer monitoring, you have this ability to understand, oh, I have a big leak here. I need to go find that big leak. Where could it be? Well, let's go to the source of the fog, and then we might be able to find it.
That's beautiful. Yeah, so it's interesting. I mean, you can hear these guys talking. They're building scientists. They're also doing forensics. They're also doing precision diagnostics. And yeah, you're not in like comfortable working conditions typically. I mean, you should hire very small, skinny people.
Yes.
So I think that's enough. So the system connects. It shows you in real time how well it's doing with leakage. Tiny bit more about the aerosol that's turning into liquid. What is it made of? What does it end up like?
Yeah, so
is there any way to describe it?
That's a great question. So we get it in liquid form. It sort of looks like watered down Elmer's glue. It has lower VOCs than latex paint. It's super friendly. When it actually sets up, there's no VOCs left. But essentially, we turn a liquid into a fog, this aerosol that goes through the system. And when that fog starts building up on the corners of things, it sort of starts to harden into a sort of like a goo, like a sticky, tacky, the thing you get on the back of credit cards, where it's sort of like gummy a little bit.
That's a good metaphor.
Yeah, and so it's a vinyl acetate polymer is the name, sort of the description of the substance. So there's some vinyl in there, some sort of plasticky substance, similar to what you would find in a mastic, I think. But basically it always stays sticky and pliable its entire life. So when we first started six years ago, we made this demo plenum. We could take it and show people how it seals up holes. And so we would, cut a hole in this metal plate and it would seal it up. So we have those metal plates from 6 years ago, and we can show people the same plate that's now 6 years old, and you can see that it's still pliable, it's still tacky. And what you want out of this substance is, if something were to come and disturb the ducts, you want it to be able to move a little bit without breaking its seal, so it can sort of last a long time.
Yeah, that's one of the problems with conventional mastic, is it's brittle.
Yeah, so it has a 10-year warranty residentially, 3 years commercially, and we know people that have had it longer than that, and it's as we've seen, I have a piece that I've played with for the past 6 years. It's still holding up great. So so I really think it would last a lot longer.
I remember for me, the defining moment from almost unquenchable skepticism, like no, there's no way I trust this stuff. Basically, they had a piece of metal or wood. It was metal, and they had said the word Aeroseal like was routed out of it with 5/8 inch wide letters. And then they put the fog through, and it gradually built up on the edges of the letters, gradually closed them up. And then there was some time they had to wait to let it harden. But within a short period of time, I was able to take my finger, like my tip of my index finger, and go like right there into those, in the middle of the letter. And it was stiff, it was rubbery, pliable, but it was strong. I was like, I'm going to pop this right out. It's like, I'm going to just knock this goo right out of here. There's no way. And that was the moment. Like, oh my God, I think this is legit.
Yeah, so as far as its strength goes, conventional units run really low pressure, less than an inch of pressure in the supply plenum max.
Oh my gosh, less than a half inch.
Right, but Aeroseal is also meant for commercial jobs too, and so its seals are good up to almost 10 inches of water column, which is crazy high pressure. Even in commercial units, you rarely see that much pressure. So it's good. The seals really, really do last. And I also do want to point out that there are other ways to seal ducts. You can seal them by hand. You can get mastic. You can caulk the buckets to the sheetrock.
You do all that.
And we do, exactly. We do hand sealing a lot as well. But I just want to point out, Aeroseal isn't the only way. It's just the best way. It's the most thorough. I don't have to worry about crawling through and getting every single last crack in the underside of some uncomfortable position to be in an attic. I can just get the bulk of it when I go up there to hand seal, and then have Aeroseal take care of the rest.
Mm-hmm. So this is our podcast. I can ask you whatever I want. There's no. So what's it cost? It's like $3,000, $2,000. I forgot.
Yeah. So the retail price is $2,450 per system.
So a contractor could just add $2,500 per installation. Boom, done.
Definitely.
But they don't.
No, I think they're trying to maximize profits, cut costs where they can, and I think also there's a little bit of pride there. They should be able to seal their ducts if it's new construction. They should be able to get them to passing without needing Aeroseal. There's definitely times where we go in and seal new construction ducts because they haven't been able to pass their test, and now all the ducts are covered up, and there's no way to get to them without taking out sheetrock or a really expensive finish that they put on the sheetrock. There are reasons why Aeroseal really does make sense for contractors in certain situations.
Oh, absolutely. There have been studies done about ROI, this return on investment, and one of the striking asymmetries in the, let's say, the home performance retrofit market is that doing duct sealing on an existing home, whether by hand or through Aeroseal, the ROI on something like that can be a few months, depending on how, meaning like you're starting to make your money back. Definitely less than a year is typical. I mean, it depends, so making sure you guys listening are knowing this depends. But, let's say on the order of a few years, you'll definitely get your money back. And your health will improve right away. Your air quality will improve right away, which over time your health will improve. And that's actually a whole interesting thing about that. If you change the air quality, you have to detoxify for a long period of time before your health improves. So it's interesting. But point is that window replacements, you see full-page ads in the newspaper because it's very profitable, and it can take hundreds of years for it to pay itself off. But people don't care. So it's like people don't know how to actually have their best self-interest at heart. They sit in their room, they're like, something's the matter with my room, I'm uncomfortable. And the first mistake is, and I presume that I can see the problem. I will look at this window and assume it's the problem. You don't see the ducts, you don't see the leakage, you don't see the layers of building science. And then the contractors, how many Aeroseals of Austin are there? There's just you guys, right?
Yeah, so in Austin...
It's not fun. It's not...
Yeah, so in Austin, there's a handful of good duct sealers, weatherization companies and things like that. The only other company, I believe, there's one air conditioning company that has Aeroseal equipment. So we're the only other one in Austin, aside from this AC company that does it.
But your company is dedicated to duct sealing and improving indoor air quality.
Correct.
Do you also do duct cleaning?
We do. We clean ducts as well. Duct cleaning was another thing that I was very skeptical about, just like Aeroseal. I didn't believe that it worked. But now I've realized with the type of equipment we use, it's called RotoBrush. It's very non-invasive. It's not going to tear up the ducts, assuming that they're in good condition. Yeah, so this brush, literally it's a spinning brush, and the idea is it cleans it through repetition. Hundreds, the RPM is so high that you repetitively do something, you're going to clean off the dirt without damaging the ducts.
So it's not scouring it.
Correct. Like I could put this brush up to my face, and it would just rub my face, and probably after 4 or 5 minutes, it might get mildly irritating. It doesn't really hurt the ducts, but it is aggressive enough to actually clean them. Because that was my thing, and why I was so skeptical is, okay, if it doesn't put holes in the ducts, well then how is it cleaning the ducts? Because it's not abrasive enough. So anyway, we've had really good luck with clean and seal packages where we go in, clean the ducts first, then we seal up any leakage that's there, and now with a good filtration system, you will never need to clean your ducts again. They can't get dirty because everything is sealed and you've got a filter at the only place where air can get in.
Interesting.
We were doing a job the other day in San Antonio, and this lady had a very sick husband. And whenever he was in the hospital, he was doing just fine. And every time she brought him home, he started having all these respiratory problems. And so she called in an air conditioning company, who then called us in to seal up the air conditioning ductwork, because the leaky ducts was making him sick. Now, he was in a very vulnerable state anyway, but when he was in hospital, he was doing fine. But at the moment he came back, and they saw this over numerous visits back to the house, and he was in the home when we were sealing up the ductwork. And, it makes you feel good at the end of the day when you know that you're going to be improving somebody's health, especially somebody in a vulnerable position like he was.
That's beautiful. So the business of building science, particularly the business of the building science of sealing ducts, you'd mentioned, Ian, that in the beginning you were getting people like this project you said in San Antonio, this homeowner that wanted to do something to improve their air quality. But now you mentioned this other type of work, that this hotel. What do you, the hotel, or not hotel, what kind of building was it? Office building?
Actually, it's a big hotel. They're just building it downtown. But they, on this one particular shaft, they weren't passing code. And they had to pass code. Unfortunately, all of this shaft was buried in concrete, not even sheetrock, it was behind concrete.
Oh my gosh.
And there's no way could anybody get to it. Aeroseal is the only way. And they found us through searching the internet and called us up and said, we want you in the next week. And we went in there this week and did it. And they were amazed at how quick it was sealed up. And it was fabulous for us because their staff had already blocked off all the taps on every floor. So all we had to do was go to the 33rd floor, hook up then climb up the stairs to the next one, and then hook up at the top.
But your equipment's big. How did you get it to the 34th floor?
There was in fact, he said to us, he said, "You're lucky. The elevator just started working last week." But anyway, we got it up in the elevator, and how long did it take? 40 minutes? 45 minutes?
45 minutes of actually sealing. Yeah, it works pretty quickly.
33 floors. What was the diameter of the shaft?
There was a lot of setup. This was just a 2 foot by 2 foot shaft, so
that's pretty big.
Relatively small.
A large surface area. That's relatively small for you?
For a commercial shaft. The shafts that I've sealed previously are like a 3 by 6 shaft, 3 foot by 6 foot. So they get pretty big. I think in answer to your initial question about sort of the future and where things are going with Aeroseal, right now we focused on residential for a really long time. Cut my teeth on really how it works and how it affects health, comfort, all of those things. And we went in for comfort issues. We went in because there was a problem. Someone was in pain. There was, mold growing on things. People couldn't figure out humidity issues. They had health issues, things like that. The next sort of step to that was like sort of in the beginning when we were trying to build traction, because like we said earlier, if it's not a water leak, how do you know that your ducts are leaking, and how do you raise awareness about these sorts of things? So from there, we've also partnered with solar companies, and so solar companies see the benefits on both saving energy and improving people's comfort. So there's the solar aspect of things that we got into, and then now we're sort of getting into more commercial and new construction. There's a couple of companies in town that really see the benefits on even new construction and remodels, as far as being able to seal the ducts even tighter than what they're capable of.
And actually, in San Antonio, we're with an air conditioning company down there that does a lot of high-end homes, and they've been brought in on a lot of projects where there was a lot of problems. They've spent millions of dollars on these homes doing big remodels, and fabulous, super expensive flooring that all of a sudden is now cupped.
Oh no!
Because there's way too much humidity in there, and it's because of their leaky ducts.
Yeah.
And they don't know how they got past that certification, because the ducts didn't change, but clearly the certification got...
You mean someone tested the ducts and said it passed, even though it shouldn't have?
Exactly. And that's the shame of it.
Yeah, it really is. And that could be another podcast, and it's something a little delicate to talk about. But yeah, compliance inspections often go to low bidders, and it's a lot easier to be a low bidder if you're passing all your jobs. Yeah, I remember a production builder saying, "You're trying to make money off me with these retest fees," which was $35, like a 45-minute one-way drive from my office. It's like, yeah, right, that's my strategy. Wow. Okay, well, I think we covered a lot. Those of you listening, we do have a dog yipping nearby, so that's just some extra chiming in on this. Any final comments from you guys? Either of you? This has been great.
It's interesting. They say that if you can survive in your first 3 years of business, then you will carry on. And we managed to get past that 3 years. Now we're really picking up some momentum. We bought our second set of equipment.
Oh, I didn't know that.
We have our second truck and second trailer. So we're ready now to sort of have other employees, and we bring on people for certain jobs, regular people that we use. But our goal is to have another crew and train them just as passionately as we are.
Yeah. And
then we'll have 2 crews on the road all the time, and that's our goal. Our goal is not to be a super huge company. We realize that we wouldn't be able to have the degree of quality that we have if we got super crazy big. And so we don't strive for that. We are looking to, have a couple of crews on the road and to be busy every day.
Fantastic. Yeah, and from the lens of building science perspective, again, kind of this bearing witness, it is astounding and somewhat, I guess I'll even say somewhat disheartening to me that a valuable service like yours that can directly impact health, comfort, durability, and efficiency is overlooked, is often not brought in on jobs where it could make a big difference. Surprising, at the very least. So thank you both for being here.
Thanks for
having us. It was a great pleasure.
Thanks, Chris.
You're welcome. Okay, that's it. That's a wrap. We'll see you all next time.